hope you guys have had some coffee your way. After lunch, it's easy to fall asleep.
We're expecting the entertainment to do that, to keep us awake. So.
I'll do a song and dance between the talks. We're in the technology session. We've got a few presentations to get through. We'll start. The first presentation is by Ned Eakin-Brooks. He's an associate professor at the University of New South Wales. Ned works in the School of Photovoltaics and Renewable Energy, and basically he's interested in photovoltaics, looking at their past and future and their promise.
Sorry. Thank you very much, folks, and thank you for having me here to talk to you. I've recently joined UNSW. I joined last August, and before that I worked in London in the UK. And my interest has been for a long time, about 20 years, has been in high efficiency photovoltaics. And so that inevitably means that my career's sort of crossed paths with people who work in space photovoltaics. I've worked in that field in a couple of space labs as well. So in this short presentation, I've got 10 minutes. What I want to do is just get across to you where we are with space photovoltaics and what we're doing at UNSW that can maybe lead to some interesting technologies. So I thought I'd start just with the problem. So this is a very nice photograph of sunrise over the Earth taken from the space shuttle. You can just see the tail of the space shuttle there. And the graph is showing you the solar irradiance. And today, the curve we're interested in is the white one, which is the extraterrestrial solar spectrum. And immediately we see that we have a challenge, because with photovoltaics we have to absorb that energy and convert it into electrical power. And so, without burning up too much of my 10 minutes, what this means is I need a semiconductor which can absorb sunlight, produce a voltage, and the amount of current that comes out of it depends on the number of photons that land on it. And so, to cut a long story short, if we look at the sort of semiconductors that we're familiar with, like silicon, we find that silicon sits conveniently sort of at this point just beyond 1 micron. So silicon's actually quite a good choice for a solar cell, and indeed the very first solar cells that were made and also deployed in space, at least in the West, were indeed silicon cells. You can still buy them. Silicon cells power things like the International Space Station, largely, and they've got some pretty good characteristics. So typically, the beginning of life efficiency for a silicon solar cell might be somewhere around sort of 17%. They're relatively lightweight, quite good power densities, and so on. But silicon has been displaced over the last 15 years by a new compound semiconductor technology, which I will tell you about. And the reason it's been displaced is because although the beginning of life, the BOL metrics are quite good, the radiation performance of silicon is actually very weak for a semiconductor. So, cutting another story very short, when a silicon cell, or indeed any solar cell, is in the space environment, of course it's exposed to high energy electrons and protons, and they damage the semiconductor. We need very, very high purity silicon. The interaction of those high energy electrons and protons is such that it reduces the collection length in the solar cell. So you still absorb the light, it's just that absorbed power can no longer be converted back into electricity. You can't collect your excited electrons. So that's why when we look at how the efficiency evolves with something that we call here 1 mega electron volt fluence, this is a sort of normalized scale for the amount of irradiation your solar cell has received. Beginning of life efficiencies might be here at 17%, but typical end of life in geostationary orbit is on the right-hand side of my graph here, and you see that you're down at about sort of 10%, 11%. And so this is the big weakness for silicon solar cells. And if anyone's interested, there's a very nice paper, dates back to 2000, but it's still very true today, on the solar array trades between the very high efficiency technology that I'm going to tell you about and silicon. So how can we do better than silicon? What we do is we partition the solar spectrum up into different bands. So instead of just using one semiconductor to absorb some fraction of the solar spectrum, we now have a stack of solar cells, and it is literally a stack of solar cells that then absorb different parts of this spectrum. And in that way, we can actually make a solar cell that can absorb the solar spectrum much more efficiently than we can with a single semiconductor. The efficiency limit for this is mathematically about 70%. So how might we make such a solar cell? This is a slightly technical chart showing you semiconductors on what we call the lattice constant. Lattice constant is spacing between the atoms in a crystal, and in general, it's easiest to make solar cells if you keep the lattice constant the same. In the case of silicon, it's easy, it's one material. In these so-called multi-junction cells, it's a bit more complicated. You need to find a family of semiconductors that sit on a similar lattice constant that span the solar spectrum. Here is convenient 3 such semiconductors: germanium, gallium arsenide, indium gallium phosphide. And this is the workhorse for the satellites that are launched today. You're actually familiar with these semiconductors. It's not just gobbledygook. Indium gallium phosphide is your red bike light. And gallium arsenide is that funny little light-emitting diode that you can't see that sits at the end of your TV remote. Germanium you're probably less familiar with, but we use it for mid-infrared optics when we're not making electronics out of it. So these are semiconductor materials which you might not have heard of up until today, but which we've got quite some expertise in the semiconductor industry. This is what a triple junction cell actually looks like. This is a cell that I've taken from Azure Space, who's one of the European manufacturers. And we see that its metrics in terms of radiation stability are superb. The beginning of life efficiency here is almost 30%, and end of life is somewhere around about 26. And this means that the sort of power density here is only dropping by about 50 watts per square meter. So whereas with silicon, if you were to launch a 15 kilowatt satellite, you'd need over 100 square meters of solar array. With a multi-junction technology like this, you're talking about 40 square meters. And if you're concerned about the cost of your launch, as most large satellite manufacturers are, then this is what has driven the industry to these expensive but very high performance solar cells. Now in my remaining few minutes, I want to tell you a little bit about innovation in this area and what we're doing at UNSW. So right now, the technology that's around the corner is something called inverted metamorphic. And one of the remarkable things with this is it improves that multi-junction technology. It actually removes the germanium from the stack and introduces a new semiconductor into gallium arsenide. And the clever thing here is not only does it increase the beginning of life and performance, but it's also flexible. It's a very thin technology. And so the power density metrics have gone up slightly, beginning of life metrics now 32%. There is still an issue with radiation stability. It is not as strong in the radiation environment as the standard triple junction solar cell. That's one area where we're going to have the opportunity to work with some colleagues in Japan to try to strengthen the radiation response of this particular technology. I think probably don't have too much time to go into details on how you make this, but what we've done is we've swapped out germanium, and instead we've actually moved to a different lattice constant. And there's some technological complexity in doing that, but it's feasible and it works well, such that you can make these flexible arrays. And right now the emerging market for this type of cell is not quite yet in space, partly because of that radiation stability issue, but very much on these UAVs. So this is the Airbus Zephyr UAV. It flies at 65,000 feet and is powered by these flexible cells. It's the first major market opportunity for this so-called inverted metamorphic solar cell. What are we doing at UNSW? We've got an Air Force-funded research project. I should acknowledge the European Space Agency, who kicked us off a couple of years ago in this area, where we're making solar cells that are super radiation hard. And we do that by making the solar cell very thin. If we make the solar cell very thin, we need to introduce something we call interstitial light trapping, where we introduce a grating into a multi-junction structure. To cut long stories short, notice this black line. This black line is what we calculate would happen if we make such a structure. These dashed lines are typically what you get with present commercial technology. So end of life in geostationary orbit here is about 10 to the 15. You notice the black line hasn't changed very much at all. So this is going to take a bit of time to develop, but it's the direction in which we want to go in making super radiation hard solar cells. The other big challenge is new semiconductors. We've already talked about how we've had to move away from germanium to some other semiconductor here. There's essentially a whole range of semiconductors that we can use in this area to make 4, 5 junction solar cells. And if we can do that, we'll get to efficiencies above 33%. Very conveniently, one of our colleagues in our School of Photovoltaics is Professor Steve Bremner, who has an epitaxy system which can pretty much color in this table, and in particular, we're particularly excited because he can introduce bismuth into this material. Bismuth really fills in this gap that we have between germanium and gallium arsenide. So in summary, I really want to just say that, you know, silicon right now is the technology for terrestrial photovoltaics, but for space, we're looking at these compound semiconductor technologies, something we're working on in our school, lots of research challenges. Very happy to talk to you if you need a friend doing space photovoltaics in Australia. Thank you.
Unfortunately, there's no time for questions. If you're impressed, you're interested, just put a tick next to Ned's name and you can talk to him after. All right, so